So continue with our thing before going to just so to learn the language of how we can describe that universal wave function. So we have taken some recourse or some flashback towards how we see statistics and how we understand probabilities and distributions and correlations also of variables. And in that we had conditional probabilities as well as one's conditional probabilities and expectations also in there. So as well as correlations. So in today's class we are going to have how correlation of finite distributions. Or before we are going to have a correlation, first we will have we will just talk about information of for finite distributions. For example, if we define number x with an information x to be such that if we define it that way, then information ix can be written as probability of xi. This is how we, and it can further be written as expectation of log x. So you can see, so we are using the information, the Shannon information, how we define this thing. And this probability can be seen also as expectation, as a function of not only, which is not only functions of the probabilities alone, and not any particular value of probability. So in the scheme of things, so the way we just had. So once we explain Dirac delta function or any function, so the more the variable becomes sharp, to less we say it's the other parameter becomes improbable. The more the wave spread is, so it becomes more, one of the parameters becomes more probable as compared to the others. So in that context, we can say that so measure of probability distribution is inverse measure of spread. So in this respect, information plays a simpler role that of variance. You can have, so more spread is there, so less is the probability distribution, and vice versa. If the probability, if the spread is less, you can just pin down that probability distribution along some values. So it has some advantages when you compare As compared to the invariance is that we can just localize things along some range of values. In the sense that distributions can be defined over arbitrary sets. Distributions can be defined over arbitrary sets rather than I can say sorry, one second, one second. So solutions can be defined over arbitrary sets. So so variance is normally defined over a distribution of real distribution over real numbers. So as compared to this probability distribution, it can have a range of values, arbitrary range of values, whereas variance is defined for a distribution of some real numbers. So there are some advantages. And further, once we invoke this thing, it's not defined for negative values. But this is not so this is not the problem, because we are not interested in knowing the absolute values. The value of negatives cannot be defined here, is because we are not interested in the absolute values. We are interested in the how between certain range of values or certain difference of values, the way we define these quantities in that sense, or rather differences. We are interested in differences of values along certain range which will correspond to those distributions. So if we for information for a group of random variables x, y, z, which are with joint distributions, probability of xi, yj and zk, and those can be denoted as x, y and z, such that this is equivalent to probability of values xi, yi, zk log of probability of xi, yi, yj, zk. Now we come from this, we can have the definition of expectations, which is denoted by, if you remember, expectation is denoted by you are taking a marginal distribution or a large values, marginal distribution among the whole of distribution, and multiplied by the numerical values or numerical values along some range of real numbers, or along some range of some Cartesian products which belong to x, y, z, so on and so forth. So in that definition, if you remember, expectation is along f is denoted by y, k, z, l, f, k, l, z, l, where this is the
marginal distribution of that thing among the distribution, and this is denoted as a numerical valued function defined on the elements this which belong to x, y, z, so on and so forth. So this is the way we define expectation. So in this sense, so we can say this can be defined as information for a group of random value variables can be defined as expectation of log of this px, I, yj, and zk, which immediately follows from our previous definitions. Since the range of since the group of random variables x, y, z, and so forth may be regarded as single random variable whose values are defined in terms of Cartesian products x cross y cross z. So these values, they belong to these individuals, so on and so on. Now we come to something, another idea, which is called as, which is also called as conditional distribution. Sorry, conditional. So the way we had information, we can have conditional information. The way we had conditional probabilities. So we are not interested in, we are taking a variable in the larger set of variables, and that variable, the value of that variable may be independent of the total other variables. So in that sense, or other probabilities. In that sense, you can also take conditional probability, you can also relate it with the conditional information about a system, which can be written as I going from x, y, z to b. This is given by I, j, probability of xi, yj, zk. This is log of log of probability of b and xi, yj, and zk. Now you can write this thing as an expectation of omega n. Now log of pvm omega n xi, yj, zk. Where you can say these are the particular values. Particular values of these things. So for independent random variables, x, y, z, we can easily prove that information in system x, y, and so on and z can be ix plus iy plus so on and so forth. So it means that so if the events are unrelated, so total information about the whole system can be written as the sum of informations of those individual subsystems in that sense. So that's intuitively conditional information. So any system, the total information of the system can be, if they are not variables or not somehow related, you can see they are as if total addition of the individual informations of those subsystems in that sense. So now we come to the thing called, which we talked we talked of as we can talk of correlation for correlation for finite distributions. So now we can again so you can say correlation for finite distribution. So in that sense, suppose we have a pair of random variables x and y in a joint distribution. Probability of xi, and where we say x and y are correlated. In which we intuitively mean that one learns something about one variable. Correlated means that we can know about this variable, something about this variable if we know y, and vice versa. So y and x and y are related. So if you know about something about x, you can in turn know about y, and vice. If you know about y, you can know something about x. So you can see that thing. So if we are not informed of the value of y, then our information concern x is. So if you are not informed about y, one of the variables, so this information can be got from the idea of marginal distribution. Yes. However, if we know the value of y, one case is you don't know y, so we can know this information from the idea of marginal distribution, the total number of the distribution among the whole of distribution. So you have to take only this thing in that sample space. But if we, for example, now one is that you don't know y, so you can then find, you have to independently find x from a marginal distribution. But the other point is that if we say that y has value yj, then our information about x changes to the information of, so we'll have something called conditional distribution. So the conditional distribution is P of y j xi, I of yj x. So we wish that our degree of correlation will say about how the two variables can be correlated. So it's also not. So it's also a thing that if two correlated variables, so whether they are correlated in some specific sense, in certain range of values, or they are correlated along broad range of values or numbers or particular value. So we have to give the single number to measure. So we have to provide a single number to measure the strength of correlation. To give us the expected value. If we know y in some conditional sense, so we could, along some specific value, we should be able to specify the value x in that sense. So it's called correlation. Correlation x and y, which is denoted as x, y. So x and y can be written as expectation of yix minus expectation of x is expectation of yix minus I of x. So you have to expand this using 2.3, using 2.3, 2.1, the last one. So we have to have the idea of this conditional information. To have this correlation between x and y, because we have to choose a particular value of y in a conditional way, which will somewhat give us some specified information about x in that sense. So x of y, it's this thing. This is the general thing, or yes. So expectation of I along y, I along a range of values is basically expectation of yj log of p of yj x of I. So it's the information we are interested in. So we can say that expectation of log of this p of xi yi minus expectation of log of p of I yi. Oh, yes. Or you can write it as I of information about x and y minus information of y only. Yes. And if you combine this and this, this and this, this and this, we can say that correlation between x and y, correlation between x and y can be written as ixy minus ix minus iy. So you can say it this way. You can have this value of this here, and you will get. So this is how we can define this. So the correlation is symmetric between x and y, and hence also equivalent to the expected change of information y that will give. Again, this correlation amounts to the sort of missing information we possess in marginal distributions. That's loss of information if the variables, if you choose that variables are not dependent. So if the variables are not dependent, they are independent. So this amounts to that we will lose some information about the system, because if the two subsystems are not correlated in this sense, yes. So on the whole, you lose information about those subsystems. Now, so in the some sense, once we correlate the variables also, one thing is that correlation of variables. Maybe, for example, if a person is, if a if a if a group of two, what I should say, variables, maybe having some joint a property which is common, in the sense, for example, they may be male also, or they may be having political beliefs, having predilections for belief systems towards a particular, for example, a political party. If we can correlate them, that if there is a set in which we talk of correlation of human beings, in which human beings also you call of males as well as females. So, for example, if males having set of males having more predilections or affiliations for a particular political party. So it's that we implicitly assume, once we correlate things, we assume that there may be some variables by which you can we relate them. So it's a difficulty. So whether if political parties are, for example, males having predilections for particular political parties, affiliations to, and being males, so it compounds the thing for so they may possess nothing of the thing, nothing of qualities like variance or covariance. So once we talk of correlation and joint distributions, so you have to take these very factors into considerations. What parameters in a correlated distributions, and what are the conditionalities? What is the conditional probability? Which set of parameters specifically between two random variables they are related to make things precise, to make correlations meaningful or justified in a given distribution. So there can be now, so apart from these things about correlations, there can be some useful formulas which will help us to, or other inequalities also, which can easily be proved. For example, you can have conditional correlations and conditional superscripts which can be defined like this. Can be defined as expectation of log of probabilities uy, vw, vj, wk. This is probability of ui, probability of vj, probability of wk. In the same way, you can also have conditional correlation, which can be accordingly shown like this. In conditional correlation, you can have expectation outside, such that if it's this thing, for conditional correlation, we have x, y, xi, this is yj. We can go it for expectation of along variables yj, again log of pxi, yj, uk. So we can just see it, we can define xi, y, uk, xi, yj, and omega m. This is a conditional correlation. One is correlation in the sense, general sense, the other is the conditional part of the correlation. You can see it. So we are going to just enumerate and write different form different relations, elementary relations in these correlations. So I'll write it here for the sake of so you can have for example, which you can prove also, for example, if there are variables u, v, so you can write it like, you can write, so these are commas, you can have this thing, you can write it like this, plus u of v. So if you want to remove comma, so it's comma here, if you want to remove comma, so you can have u, v, w, can be written as u, v, w, can plus u, v, w, it's comma removed. So in the same way, you can have correlation of x is no definition of no commas. Or removal of repeated commas, you can write it this thing, this x, x, v, can be, we can have x, v, so we have just what I should say, absorbed or eaten with this one of the thing. We can also define self-correlation as x of x is I of x. Just like we have a set and dual set, you can map a set to its own identity thing. Self-map, you can see it, you can say correlation of two random variables, you can denote it like this. But here you have a minus. This is also called self-correlation. Or you can have u, v, w, x can be written as omega j. It's u, v, x. Or you can have x, y, z can be written as x of z. Or you can see x of y of z is greater than, so x of z, x of y, y of z minus x of y. So you can see for any random variable w, for example, can be replaced by x, y, or z, and the relation holds since the set is so we can have the set may be regarded as a single random variable w, which takes the values in those sets which we have defined as chi cross of y cross of z, so on and so forth. The way we have defined expectation. In the expectation, one part of it, if you remember, we defined as We defined as expectation as P of y. Expectation we define like this. Expectation of f we defined as this is the marginal distribution, and f we defined as the Cartesian product, which might have some numerical value, and these elements belong to those chi's, that Cartesian product, which is chi x, y, z, so elements of those Cartesian product, and this is the marginal distribution. So we'll in the next class. So we have done this much. Again, because these properties are going to use in our formalism. So in the next class, we are going to generalize and see further some of the properties of correlation, which we might need in future.